Yeah, welcome to the webinar System Debugging using Cross-Triggering Features. My name is Ernst Wielage from PSE2 Germany, and in this hour I will show you the essential steps how you can use a debugging feature with more values, specific on the software and on the hardware side to combine this with cross-triggering features. So here we see the agenda of our topic today. So an introduction to cross-triggering, and then we go through the different features which are dependent on the platform we use. So actually Zynq 7000 system on chip, Zynq UltraScale MPSoC, Versal devices, or even legacy FPGAs, where we have a processor by using the soft IP core of a microblaze. And we have nowadays also the RISC-V variant of the microblaze available. And for all of these, cross-triggering features can be supported. We will go through the steps how the Vivado project needs to set up as far as we would like to have logic analyzer support on the programmable logic. We will see then the cross-triggering enable on the Vitis tool side. So this Vitis debug environment have a prepared feature which can be enabled and can be set up for different purposes, how cross-triggering can be used. Then I will show you actually the environment where we can launch the logic analyzer, and obviously to combine this by cross-triggering with Vitis debugging so that we can use both tools simultaneously. And this is shown then in the cross-triggering execution. So using the logic analyzer of Vivado and using the software debugger in the Vitis IDE. And a short wrap up. Okay, so regarding a short overview, introduction to cross-triggering. Yeah, this module introduces the joys of debugging using cross-triggering. And when dealing with embedded systems, it is often difficult to determine the origin of the problem. Is the problem in hardware? Is the problem in software? So actually, we need tools in heterogeneous platform designs where we have hardware, programmable hardware, analysis, and software analysis tools. And cross-triggering techniques offer this mechanism to help identifying this vendor. Starting with a review of the hardware and software debugging techniques, the high-level approach to cross-triggering is introduced here. And we will show you here the mechanics of the process in details for the different target platforms. So actually with a processor and programmable hardware. The Vivado design suite includes the Vivado analyzer tool, which is the logic analyzer here. And this tool using sampling IP that you include and to connect signals of interest, probe signals, in your programmable logic, displays the capture signals as waveforms. In its primary interface is via GUI. However, its support scripting is as well supported, which is a powerful capability for automating test procedures. It's worth a moment for brief diversion to note some interesting use case as the tool is capable of more than just waveform dump. And we have options to enable even multiple logic analyzer cores. We can have virtual I/O IPs in use to observe pseudostatic signals, virtual LEDs, for example, and where the debugging of the process, at least track downs unwanted behaviors, validation checks that the proper response are being generated at the correct time. Data collection requires the ILA course, so the Integrated Logic Analyzer course. And VIA course provides observing states without capturing data. And this is quite important as it also requires some resources in the PL design, like block RAMs. These signals collected during debugging may be used during validation as known good data to ensure that whatever changes have been made to the design do not negatively affect the generated results or as real-world samples to continue testing the design against. And since these samples are captured, they can be played back or even modified to generally useful corner cases when offered as a stimulus back to the design. So therefore, it's a wide range in which way you need your validation concept, but actually the ILA core here is quite essential. In the field of cross debugging, we have processor context and programmable logic context. So when we go with ARM IPs, these are provided in silicon processing systems with Zynq SOC, with Zynq UltraScale MPSoC, with Versal devices. But in addition, you can have even purely programmable logic when your processing system is also built as soft IP environment. So actually, it's here the intention that we have on the one side, a processing system, and on the other side, legacy programmable logic, where we need IP cores to bring into the hardware design, to observe, to trace the signals, and on the other side, to have tools of debuggers or profiling environment, where in that context, purely only the CPUs are seen. With ARM technologies, the core site architecture of ARM is seen inside of the processing system. And this can be connected to debug ports, mostly used with a USB cable, but actually also even more interfaces as far as wider data throughput, high bandwidth are required. So actually we can have access control, legacy, or we can have even also trace support, which means to observe the running system. In that context, you will finding also even partner tools, but in the pure silicon, we're finding different capabilities, how connectivity and debug access is provided. Here, I will show you actually how these core site technology features can be used for cross-triggering when we use purely the AMD tools, so Vivado and the Vitis IDEs. Yeah, and here is the Vivado Logic Analyzer GUI scene. Is comprised of two portions. The first resides in the hardware itself as IP block implementation, so ILA or VIO, or even multiple instances of ILA, even also multiple instances of VIO is supported. Yeah, and the second part is the user interface of these blocks, and the user interface is the IDE, which can be found simple in the Vivado GUI context. You can launch this context as a task, or you will find that context also in project-based mode when you have a look to the flow navigator. The EILA IP samples one-to-many signals simultaneously, and the VIO core can both inject signals, so virtual input as virtual output, so that the remote user can activate or change modes within the design and sample status signals. So I will not show you the features of VIO here. So in the slides, you will see here the use of EILA, but actually you can even combine probes with many different instances as far as you provide resources for these IPs. Yeah, this second element, the user interface, is on the one side the hardware structure you see, where instances of EILAs or VIO cores can be seen, and on the other side the control panel, where our logic analyzer can be seen in its status. So for example, here I see an idle state and a control menu bar where at least the signals can be observed in the waveform view or in the panel view of the VIO. The EILA runs at full speed, so actually this is a real-time capturing, but on our host PC we have a JTAG-based slow interface where captured data can be streamed out in the synchronization of our host PC. The capability of cross-triggering requires trigger signals. So here we are quite flexible when we see here that optionally trigger signals can be enabled on the external side or can be enabled with the EILA internally. So therefore blue signals here are shown as optional extensions, but with the probe signals you use, you can by default even use these sample signals also for triggering. But in this way and in that way can also be exclusive if you like. So which means you can also define signals which are purely only used for capturing or even purely only used for triggering. By default, both sides will be enabled. The EILA trigger signals are not captured. This means actually we see that those ports are purely in use with a trigger detection unit and not for capturing. Capturing requires memory. Memory resources are used with your design. And here we see how the processing system can be connected with the EILA configuration. So for cross-triggering, you would like in using both tools, a software debugger for the processing system, where you have at least a context of a CPU, and on the hardware side, a logic analyzer, which have the capability of cross-triggering by enabled trigger ports. And then we can simple wire this up. This is an on-chip wiring, so which means in the programmable logic on the FPGA side, you will connect trigger ports of the EILA with dedicated ports of the processing system, and the core side debug interface makes it quite flexible that this can be used in a great, let's say, really capability, which means for each individual CPU, you can have also selective trigger ports, for example. And as far as we have a soft implementation of CPU, we will have then also a soft debug unit, the MDM component, which also can be configured for trigger dependency to the processing system, which is typically here a microblaze soft IP. Yeah, the VIO, the virtual input output block, does not have memory. This is a customizable component capable of monitoring and driving internal signals in real time. So for our inputs, like the size and the number of probes can be configured. And you can even drive output ports. So which means from our host side, we have our JTAG interface and we can assign signals. We can also change signals in that context. This IP block have also a clock synchronous architecture. So this means actually if we are asynchronous of our host side, those signals will fulfill timing conditions of synchronicity to the connected clock. So which means actually perhaps you have 2 different clocks in our design or even more, then you can even use multiple VIO cores to bring each probe signal into the required synchronicity as it needs. Unlike the ILAC core, this doesn't need necessarily on-chip RAM, so block RAMs. Instead, it presents and captures data on the design clock, which is linked to this clock signal. So you can insert virtual input-output signals. The size is maximum 256 on each port, but even you can have multiple ports in use. So probe in 1, probe in 2, and the same on the other side. So actually for many signals, you can use also the VIO core. Now we come to configuring the cross triggering. So we have seen what's needed at least to prepare the hardware by using these specific IP cores, and also that opportunity of debug architecture in a processor context. And for the different platforms, for the different devices, we have here a list of the processor CPU cores. Also the R5 cores are here available for MPSoC devices, for Versal devices. And you will finding in the Vivado context the IP configuration where debug cross-triggering can be enabled. And this looks slightly different. So this slide will help you to identify where you will find this cross-trigger interface. So actually here for Zynq UltraScale MPSoC, there for Zynq 7000 SOC, or even using the microblaze soft IP. And here's a differentiation of the microblaze we have in the, let's say, over 20 years now, but actually new is the microblaze 5, the RISC-V CPU architecture. And the cross-triggering feature looks a bit different. So which means for the microblaze soft IP, cross-trigger is supported with the MDM IP core, with the microblaze debug module. But for the microblaze RISC-V, you will find this essentially on the CPU core itself. When you enable discrete ports, you will have also these cross-trigger signals. So sometimes you see it directly in a context, like here, and sometimes you need to find this specific at the CPU side. But the cross-trigger signal is available for all of these processors, for all these AMD technologies. Yeah, and here we see a slide where Zynq UltraScale MPSoC is in use. There we have IP integrator block design with Versal, and this might be a starting point, which have some essential functionality. So on the one side, the memory and peripheral capability of the processing system itself. This also is configured with a SIPS module in Versal, and then some services in the programmable logic. So here a GPIO connected via an interconnect to the processing system AXI port. And the same is seen here. Here GPIO connected with an interconnect to this NOC system, which is also the interconnectivity in silicon with a Versal. But therefore, this is somehow the same demand from view of the programmable logic, but actually the specific processing system dependent on the target technology. And how can we continue? Yeah, this is this would be, let's say, perhaps also for some of you interesting to see this with Zynq 7000. It's quite simple. So if you replace the Zynq MPSoC processing system with Zynq 7000, it looks the same. But for all of them, you have the customizable option. And in the context of PSPL, you'll finding cross-triggering options, which are by default disabled. So it needs to be enabled. And therefore, first of all, you find the PSPL configuration. You will have a look for cross-triggering features. We enable the checkboxes, and we have a selective support, which connectivity profile is for us available. First of all, we see the situation before, but after you have enabled specific cross-triggering signals, the profile of the icon will change, and you will finding then the signals like, for example, here shown PSPL trigger, PL-PS trigger context. So on this slide, I use now Zynq UltraScale MPSoC. So search and find is sometimes a bit different, but actually you have also here search context, for example, when you would like to simple look for cross-trigger labeled features. And again, we can enable selective I/O ports. And so you can play with 1, with 2, with 3. The intention is, for example, when we have here 4 inputs, the APU have 4 CPU in this architecture, and therefore it would be helpful if each core have its own cross trigger. That's the reason of the number 4. Yeah, and the icon in the IP integrator will show us then our enabled cross-trigger signals. So here you will typically identify to have those signals it needs. And in this complexer ARM core site structure, you can find the groups of trace ports, of trigger ports, and somehow also more legacy FTM service, which are fabric trace macro cells. And those fabric trace macro cells are implementation of AMD Xilinx, as this will be connected to the core site debug architecture internally. So therefore, here a group of FTM will appear. And in this case, there's also, for example, a register available in the core side architecture. Yeah, but essentially for cross-triggering, obviously these ports needs to be used. And if we would also use trace core debuggers from partners, for example, like a trace port which is connected to gigabit transceiver probes, we have here also a wider parallel interface availability. This slide shows here the Versal configuration, and here we have the access from the SIPs, and you can customize the SIPs. Then you can here select PS, PMC or CPM. We need to select the processing system configuration, and this dialog will appear where we have for our PS PMC a debug section. And again, we're finding cross-triggering options. And again, those ports are disabled by default, so you can selectively enable them. And you see also what will happen. You will getting those ports as a connectivity between the PS and the PL. CTI, cross-trigger interfaces, are somehow prepared in the core side architecture for us. Yeah, and we can use them as a signal access, and this will appear then on the SIPs, which needs to be wired. This wiring is somehow much more easier if the feature of bus automation wizard will be used. So as far as this, let's say, is seen, and it will be seen if from the customization you firstly have done those steps I showed you before, and a wizard menu bar will appear, which gives you access to the bus automation. And if you click on this, you will see the run connection automation. It will show you unconnected profiles, so which means our preparation of trigger signals on the processing side and the options to connect them. And it will know that the EILA connection is most valuable, and therefore this is an offer for us. And therefore you can select here what you at least see as a text string, which means an integration of an EILA core with an auto connection to the trigger import. And therefore, this is the most easy way, but you can also instance an EILA core in the discrete way and connect the trigger signals in a manual step. So therefore, in the Vivado context, you prepared actually, first of all, the processing system, cross-triggering features. You bring in the EILA core. You can do this in your own way, but you can finding typically the bus automation wizard. And this connectivity here obviously is focused on cross-trigger interconnection. And as mentioned, two methods are available. First, the recommendation, use the nice service of auto connectivity launched with this wizard, and it knows processor cross-triggering features. Perhaps it is not always seen, this block automation wizard, for example, for RISC-V, for the selective IP call, as I mentioned, I will find the external signals, and I'm quite sure that there we have not the availability of this block automation wizard. So therefore, at the end, it is always possible that we have a manual wiring for our IPs of trigger ins and trigger outs, and therefore to connect the ILA trigger in with a processor trigger out and connecting the ILA trigger out to the processor trigger in, quite obvious. But you need to make sure that your ILA core have enabled trigger ports, and this is by default not provided. So if you simply take an ILA core from the Vivado IP core catalog, you will first of all see the essential probe signals, but not the optional trigger signals. And therefore, you will customize your ILA core and enable the trigger in. You can selectively enable this on the input side and or on the output side. But this is also a step which is automized when you use the bus automation wizard, which makes it obviously simpler for us. Yeah, in the manual way, we have also to make sure that we connect the clock to the proper clock domain, that the reset is also connected to this normally required synchronous reset with a clock domain. So therefore, this gives us a higher reliability when we make sure that the synchronization rules are fulfilled. So actually, these both input ports are accepted as signals in the clock domain of this wired port. So after that step, you have now here your ILA clock, your ILA core. If you like, also in addition a VIO core, where here not a cross-triggering feature is shown, so simple to observing the IO ports from our host side. This is a probe signal for this, but this is somehow the debug capability of hardware debugging. And for cross-triggering, we need this system ILA core with the features of trigger in and trigger out. But at the end, it would be also possible to define a custom trigger with a VIO core. So which means that this trigger is started from the environment of our local host with the Vivado logic analyzer. So actually, you are the master of your design and you define how cross-triggering signals can be used in a good way. So this is somehow a user customizable feature. And from the processor side, we have cross-trigger signals, in this case here connected to the ILA core. And this means that capturing can be started from a trigger which was released from the processing system. And this is typically here a context where a debugger is in use. And a debugger trigger for the output might be a breakpoint. And this is, let's say here, one example, but actually a lot of different other structures might be seen to use it. Okay, now how we can see in the Vitis IDE environment the cross-triggering feature. So first, the traditional way is to import the Vivado Xilinx shell archive file so that the processor context is seen in the platform project, where operating systems can be assigned to the CPU. And under these considerations, we can then create an embedded application component where obviously a context of run and debug is seen and is configurable. So first, we typically test this debug context, and reasonable you would like to have on the one side the core side access, so the debug access to the CPUs, and on the other side an extended I/O terminal supported, so a serial terminal, for example, for print outputs. We power on the board, we launch the debugger session, and then the software needs to be typically loaded while it's prepared in the local host environment of the Vitis, but actually a debugger session can also be connected to a running system if it's needed. So first of all, we make the system run, we test this essentially, but secondary, we can then have a look to change the debug configuration, as we see that there is an option for cross-triggering yet disabled. And therefore, we can enable this, but we see a lot of options in that context. And therefore, it's recommended that we creating a second configuration where at least a application debug session can be blocked from events which are enabled here, which is, let's say, indifferent handled from a default configuration. And therefore, I would suggest that we play with different instances of debug configurations. Yeah, the run control from the Vitis debugger, I think this is quite aware for you. So where we can run the program, where we can pause program, step over, step into the functions, restart, stop. So actually, this is the CPU environment of debugging, which does not see somehow, let's say, how probe signals are supported in the PL. So the tools are independent, and this is also the independent run control, the independent debug control. But as mentioned before, first of all, test your tools independently, and in the next step, you can combine this. And this is the intention to show you this actually how you should work. So if we assume that we have now, let's say, first of all, seen our debug connection is supported, and actually the program can run, the program can also have his verbose outputs. So what you would like to get first of all in your context, then you can go back to the Vivado design, where the prepared project, as we showed you before, is compiled, is implemented. We have our bitstream file. And in this context, you can then open the Vivado hardware manager. First of all, I would also assume that we do it independently, so that the Vivado hardware manager is seen also somehow first of all in the test case, where we, for example, play with the ILA core. We have a force trigger, so therefore just to see, oh, okay, it works. But the intention is with cross-triggering to bring this in the context also of a Vitis debug session. And there are two situations. The Vitis debug session was already active or needs to be launched to get this activity. And this activity here is meant to be a connectivity with the core side connection to our local host, so supported with a debug connectivity. And for this, the Vivado hardware manager is the essential tool to have this connectivity managed. If you would like to do this on the script-based side, it is also possible. So for example, a command like connect opens a Vivado hardware manager, but it will also allow you to connect if this is already opened, because perhaps you have launched this already from the Vivado context. So the nice thing is it's not a necessity that we start one or the other in this specific sequence order. So it should find the connectivity even also if the hardware manager port is already open. And in the context of the hardware manager, so here from Vivado, we go through this dialog. So open that context. You can do this in an automatic approach, or you can also configure the specific details, for example, the JTAG clock frequency. But actually, this view should appear, the hardware overview, where we see our local host, the download cable or the firmware of the controller, which sits between our cable and our AMD device. And the AMD device have on the one side a processor context, debug access port, and a programmable logic context. And the programmable logic context have here an implementation of the ILA call. You see here in the hierarchical view those instances of built-in debug features like ILA and like VIO. And then you can simply open from that context a view collection, which is called a dashboard. And in this dashboard, here it's also the label dashboard scene. You have multiple views. You have a waveform view, you have a setting view, you have a status view, you have a trigger view, and therefore here as well the control and the visualization of ILA signals. Okay, so actually, if you like, you can, for example, give him a try, click here, force a trigger, and then it should directly bring in new signals. And as far as this work, you can then define a customizable trigger. And this will start from plus icon, and you see those probe signals which are enabled and which are wired up in your hardware project. And so these can be connected and these can be defined with, for example, a comparator like trigger on an edge, like trigger on state high, trigger on state low, or changing a radix for a vectorized signal. Yeah, so this is the triggering in the debugger. Yeah, and if this all works, then we are ready for cross-triggering. And this cross-triggering execution is then, let's say, on both sides available. And now we can play with it. And playing with it means that we also have in the customizable debug environment also a cross-trigger context where those specific triggers are shown in a list. And also here, an enable feature is a necessity. So for each individual debug session from the flow, you can have, for example, the trigger consideration, let's say for our Cortex A72-0 core, we can have another setup when we would use the Cortex R5 core, for example. So that's the reason that in this case, for the one CPU core, both directions of trigger in and trigger out are selected. That's these both, and two signals in the connectivity with a programmable logic. So very reasonable. 4 instances needs to be enabled, but you can have even more or less, just as you like. And in differentiation of our technology, when we use Zynq 7000, Zynq MPSoC, the slide before, we have seen Versal. This list and the labels are, let's say, somehow a bit different. So actually, those slides will help you also to identify your signal of triggering. And here, the slide which shows us again the Versal, and each trigger have a unique ID, which can be seen by a numeric value in the brackets. This Versal technology have the largest, let's say, really capability of cross-triggering, so where we have a lot of signals. Yeah, and therefore, on the one side, the global debug cross-trigger feature needs to be enabled, and on the other side, the detailed configuration. And when you work, obviously, in the IDE of the Vitis with your application, you would like to assign breakpoints. And as I told you before, those breakpoints can trigger a hardware trace. And if you like to use this, okay, then this needs to be enabled in this setting of the debug session. Yeah, very obvious. You can have here the assignment of your breakpoints with your application, and then you let it run. Continue. And on the Vivado logic side, you have done the preparation in the trigger context. So in this case, write data on an AXI port of the GPIOs is compared with the status of hex 85. And in the trigger mode section of the hardware, we have here a basic default setting. But as far as trigger signals are an option, you will find them also to be enabled or disabled. So obviously, in this case, both ways of triggers are enabled in addition. So which means on the one side, you have here trigger signals with your probe signals. This is basic. But in addition, you can use trigger signals which are somehow external connected. And these external connections are, in this context of cross-triggering, connected to the processors, as we have seen before in Vitis, in the Vivado GUI. Okay, so actually here is a counter running whenever the GPIO is written. So therefore we see patterns when it's, let's say, here somehow outputted in the serial terminal, but on a selective line, you have assigned a breakpoint. And when you're now have enabled the trigger, as I showed you on the slides before, and the Vivado logic analyzer session is open, this event will trigger. And therefore, you will see actually your software breakpoints as a trigger to your probe signals, which are connected to your EILA. If there would have been multiple EILA cores, you have individual waveform views. And for individual waveform views, you have individual trigger ports. And these individual trigger ports can also be individual connected to the processing core side. So there's a huge flexibility available. But here, just the assumption that we play with one EILA core, as you've also seen the Vivado project. Yeah, and if you have an AXI port, you can open the structure of a write channel, read channel, response channel, seeing the signals. Yeah, and the essential value is that this trigger is actually the trigger from a breakpoint. And as far as we have shown here all trigger capabilities of trigger in and as well also for trigger out, this means that you can also define a condition here from the hardware side, which is a trigger for the CPU. And this would mean that the CPU will stop execution with a hardware trigger. And therefore, you can work in this way in both directions. Yeah, so therefore, here I've showed you a lot of slides with screenshots so that you, let's say, really be able to identify the settings it needs in usage with Zynq 7000, Zynq UltraScale MPSoC, with the same way as I mentioned microblaze, but not so many slides as far as it's only 1 hour here. But I hope actually that this will give you really a good understanding how you can work with your projects, and with a cross triggering, this is really adapted to your needs, while we see that all of these signals are never automatically enabled. So this needs to be done in a step-by-step approach, somehow a bit supported with bus automation wizard, but at the end, let's say very obvious to be checked. Does this fulfill my demand? And if not, I can change it. And this change is quite fast in the environment from Vitis IDE, because this is software controlled. But if we need other hardware signals, other probes, obviously, a rerun in the Vivado design is obviously that necessity. So this takes a bit more compilation time, obviously, but gives us the capability for each signals at the end. So therefore, you can have really, let's say, well-adapted debug sessions for complexer challenges. Yeah, so far at the end, you're welcome to ask questions, but you can also have a look on our website. So the pictogram will help you. You might save the date for the FPGA conference in next year, which is already be assigned on the 1st to the 3rd July. Or even, let's say, if we might assist you in development services, so you're welcome to contact us. Thank you very much for your attention. Have a great time. So actually, now at the end of the year, you also should celebrate nice Christmas and enjoy perhaps with your friends, with your family, a relaxed time. But for those who have questions for me, so actually you can here use the panel. So I see actually one response. Thank you. So I say also thank you very much for your attention. Have a good time, and I'm happy to have some of you back, perhaps in a webinar or even a face-to-face training. Goodbye.